push that rock here with some math. Let's look at this improper integral. It looks like a regular definite integral. It has these definite limits of integration. So the domain is bounded between 2 and 3, the domain over which we're worried about the area. But a casual look at the domain of the function tells us that there's a discontinuity over this interval. So anywhere between, if you see 2 to 3 here, then anywhere from 2, including 2, 2, 3, including 3, and anywhere in between, the function must be continuous for it to be a proper integral, because we can't integrate discontinuous functions. So we see that at 2 squared would be 4, minus 4 would be 0. We'd have 0 in the denominator. So we know by looking casually from having a great algebra teacher, our freshman year, we know we can just look at this and instantly see, oh, 2's not in the domain, neither is negative 2, but 2's the relevant thing here. So we go to the trouble to graph, and remember on these improper integrals, if I do not see the area that we're trying to compute at the very beginning of the work, I'm going to stop grading. You have to show me this area. So go through enough work to graph this over the relevant interval of values. So from 2 to 3, I graphed it, and I see that as x approaches 2 from the right, as we go to 2 from the right, this function, 1 over x squared minus 4, goes to infinity. So the area is unbounded. The domain that we're interested in is bounded, but the area over that domain is unbounded. So we have an unbounded integrand. The integrand is this function here. So see, the function is unbounded. It goes up and up and up and up and up, okay? So it's an unbounded integrand, and that makes this an improper integral. Now, this is a easily done, well, I don't know about easily, but sufficiently done integration by trig sum. So I don't want to walk through all that in this video and make it unnecessarily long, but I did the work here. I let x equal 2 times secant theta, because this 4 tells me the constant is 2. And I got the dx, which would be the derivative of this, which is 2 secant theta, tan theta. I solved for sec theta and got x over 2. Then I set up my triangle. And if sec is hypotenuse over adjacent, so I put the x, which is over 2, I put the x as the hypotenuse and 2 is the adjacent, found this leg. I realized that cotangent would be 2 over this. Cotangent squared would be 4 over this without the radical. And then I took a fourth of cotangent squared to get 1 over x squared minus 4. So I could replace this with 1/4 cotangent squared. I could replace dx with the 2 sec theta tan theta d theta. I integrated. I had to use go bananas or plantains with cosecant. And I ended up with this function right here. I was over here rationalizing. There's no reason to rationalize. I don't know why I was doing that, and I got carried away with my own work. So there's my antiderivative. So when I'm going to solve this problem, I always do the indefinite integral first, so I know what the antiderivative is. It's already complicated enough because you're going to be dealing with a limit. So we're ready to handle this now. And I have to set up a limit as a dummy variable goes to 2 from the right, because that is where we have our blow up, okay? And I then put the dummy variable here because 2 is where the issue was. And this is the problem we're trying to solve. And I have to deal with this inside here first and then the limit. Okay, well, that's why I wanted to already have the antiderivative ahead of time. So this step is not too bad. The antiderivative was -1/2 times the natural log of the absolute value of 2 plus x over the square root of x squared minus 4, okay? And I don't need the plus c because this is a definite integral, and we're doing it from m to 3, okay? So first thing I do is plop in 3. So I get -1/2 times the natural log of the absolute value of 5 over 3 squared is 9 minus 4 is 5, and it's under a radical. Okay, then I go minus -1/2 times the natural log of put in m. Well, m is just the same function, only I have a new variable, so yeah, just switching variables on myself. Okay, and then we're looking at the limit as m goes to 2 from the right. Now, I'll distribute the negative. That'll be nothing to distribute. I'll make this double negative plus, okay? But here, the limit of this is just a number. It's a weird number, but it's a number. I'm not even gonna bother to figure out what it is numerically. But the limit of a number is a number. So this is some number, call it, I don't know, n. But when I take the limit of that number, I get n. So the limit of a number is a number. So I get n there. Plus, because of this double negative, and you can kick out a half when you, I'm busting up the limit, because you can bust up limits across plus signs. But you can kick out scalar multiples, so I'm kicking that out. And I have the limit as m goes to 2 from the right of this function whose variable is m. So it all comes down to what is the behavior of this function here. And that's going to require some work. Again, it's going to require some graphing work. But we can already see that it's probably, that's really why I was doing the rationalizing. I multiplied the top and bottom by the square root of 4, and then I factored the bottom and got it to cancel. But it didn't make it any easier to graph, so I'm not sure it was worth any effort. But we can probably see that, or suspect anyway, there's again an asymptote at 2, because we have this, it is slightly different. This time we have a square root down here, and then we have some line up top. It's slightly different than before. But it turns out, if you look at the graph, it turns out that it looks very similar to the original graph we started with. At 2, there is an asymptote. And I'm just looking at the graph, I should say, of just this inside part. I'm just looking at y equals 2 plus m over the square root of m squared minus 4. Because if I can figure out what the argument of the log is doing, that, if it's approaching a number, well, log of a number is a number. But if it's not approaching a number, then the log of infinity is infinity. So I'm going to look at the graph of this, and sure enough, it doesn't take a lot of work. You put in like 2.1 and 2.1 here, and then you get 4.1 divided by whatever you get here. But it turns out it's a kind of large number. If you put 2.01, it's even larger. So you realize, again, we have this situation where, now we're not shading an area this time. We're looking at the limit of this function. What's happening to this function as m goes to 2 from the right? What's the behavior of the function? So no area this time. This is not an area diagram like we started with. We're trying to compute a limit. Well, we see that this is going to infinity. Okay? Now, if that's going to infinity, then Dirichlet tells us that the log of infinity is also going to infinity. Remember, he said, the quote is, logarithm marches to infinity with dignity. So if you have the natural log of infinity, that too is infinity. So that tells us, back to our problem here, that, hope this is still on the screen, that this limit is infinity. So we have n plus half of infinity is infinity, so it diverges. So this improper integral that we started with is divergent. Math made simple. Simpson Math.